Welcome to homework.
We have an electron moving at a finite barrier potential with some kinetic energy, 5.5 electron volts. We know the height of this potential barrier of 10, it's 10 electron volts. And we actually know we're asked to find the width of this potential bump, given that the tunneling probability is this fraction of a percentage probability. So for our equations, we're actually going to use the transmission equation. Recall this is a approximation to get the transmission probability given these various factors. It's this exponential involving two parameters, g e to the negative 2 kl, where g is defined as 16 naught 1 minus e over mu naught, and e is just the kinetic energy of the particle, in this case an electron. And we have our kappa, which is root 2m e minus, or u naught minus e, all over h bar. So we're actually given t, have everything we need to get g. So really what we're going to be trying to manipulate is what's in k, I believe. Oh, actually, no. We know g. We'll be able to calculate g and k separately if we want, or just plug them into the main equation. We're looking for L, so we need to isolate L. All right. So if we start out with t equals g e to the negative 2 kappa L, it's relatively straightforward to isolate L. You can just do some natural logs. In this case, L would be negative 1 over 2 kappa natural log of t over g. And we can just straight compute what t and g are without much issue by plugging things in. For kappa, we'll end up with 1.09 times 10 to the 10 inverse meters are the units. For g, we will end up with approximately 3.96, and this is just plugging in our energies that were given to us and the mass of an electron and h bar. So plugging these k and g values in and the tunneling probability that we already have, t, we can simply get a value for L, which will be 3.06 times 10 to the negative 10. So it'll be a fraction of a nanometer in width will be required to get this tunneling probability. It's pretty small, but it actually is. In some modern applications, you're starting to see widths this small in the nanoscale that are actually going to start becoming a problem for tunneling. And really, that's it to this problem.